valid address.
Yeah, yeah, that'd be not so good, huh? If you do good. How about Erica? How's the laser life for you?
I also thought it was okay, and I also had a bug with the copy in, copy out, but got that resolved. So yeah.
Good, good, good. Yeah, I think it's one of the tricky cases that you might not think about when you start programming. But luckily, user tests will find it for you. How about Caroline? Okay.
The lab is going good. I haven't finished yet, actually.
Oh, yeah, so worry about copy in, I guess. But you should.
Listen for today.
How about Kendall Garner?
I think for the most part, it was not too bad. For me, probably the weirdest part was just trying to figure out when it went below bounds of the stack.
Mm-hmm. Ah, yeah. Into the guard page, basically. Good, good. Okay, well, so it's about time to get started. So welcome to the next lecture in SO81, wherever you are, in whatever time zone. So today's lecture is about locks. And you probably have seen locks in previous classes, or at least been in touch with them in some way or another. And so this lecture is a little bit of a conceptual lecture, may overlap a little bit with some things you've seen before for locks, but we'll have a little bit more of a kernel and OS focus. And that changes a couple things. So just to get started, let's just remind ourselves why we need locks. And I guess the starting point is really that applications want to use multiple cores. And they want to use multiple cores to get performance. And so if an application actually wants to runs on multiple cores, presumably it wants these cores, or the parts of the application may invoke system calls. And so the kernel must be able to handle parallel system calls. And that means that, if sort of these system calls run in parallel on different cores, they may actually access shared data structures in parallel. And as you've seen by now, actually x86 has quite a number of shared data structures, whether it's the proc structures or ticks, or later we'll see the buffer cache. There's actually a ton of shared data structures. And so if you have parallel access to a data structure, and one of the cores is a writer and the other cores is a reader, we need basically locks to coordinate these updates to the shared data structure so that readers see a consistent view. So we need locks for controlled sharing, or for correct sharing. Now this is in some sense a little bit of a bummer, because we want this parallel access. We want to run multiple system calls in parallel on different cores. But unfortunately, if they share the data structures, they need locks, and locks serialize basically operations. And so, in fact, locks in the end can limit performance. And so we're sort of in a tricky situation where, for correctness we need locks, but for performance they're not good. But sort of it's going to be sort of a fact of life, and we'll see what one can do about it. But that's sort of the top level scenario here. And maybe just to really bring this point home, why do applications actually want multiple cores? And that really has to do with sort of technology trends over the last couple decades. And there's sort of this classic graphs that sort of make these points. So let me pull up one of them. There's a little bit of a complicated graph, but there's years on the x-axis, and y-axis there's units. And there are different types of units depending on which line we're looking at. But the thing that really to look at is that what has happened in the last couple of years is that, or the last decades, is that sort of starting in the 2000s, that the clock frequency hasn't really increased anymore. So basically this has plateaued or constant. And as a result, basically single thread performance of a core also, basically has reached, sort of a limit, or plateaued. And yet, on the other hand, the number of cores, or the number of transistors is still has been increasing over the same time period. So if you can't use transistors to make a single core sort of run faster, the only other option basically is to have multiple cores. And you see indeed that sort of starting from 2001 or from early 2000s, the number of cores has gone up. And so there's an application wants more performance, can't rely on a single core. It basically has to exploit multiple cores. And also this means if an application is, kernel intensive, OS intensive, where it's like a server, then that means that the operating system also has to be, run efficiently on multiple cores. And so that's the main reason, that we're sort of very interested in, parallelism, within the kernel. Any questions about this? Okay, I assume that you've seen some of these graphs before, but it's good to remind us, what the starting point of all the discussion is. So why locks? I already hinted at this. They're there for correctness. If we have readers and writers, accessing a shared data structure, and the thing that goes wrong is that we want to avoid race conditions. So if we don't have locks, we run the risk, if we have shared data structures, that we're going to have race conditions. And it turns out that race conditions are pretty annoying. And so just first, we get a little bit of sense of what it actually is. Let's look at let's create a race condition in XV6 and sort of see how it actually shows up, and then understand what actually happened. So here's our the function k3 in calloc.c. So this is the function that frees after you free a page, it puts it on the free list. So the kernel has a very simple data structure to keep the free list of all free pages, so that when calloc needs a page, it actually can grab it from the free list. And as you see here, the allocation has one. The memory allocator has one lock, kmem lock. And here it actually updates the free list with a page that just has been freed, or with the argument to free. So what we're going to do is just comment out these two acquire releases that basically mark the acquiring of the lock and then releasing the lock. And so this piece of code that sits in the middle that used to be there's now is not being executed anymore atomically. So let's do that, and then run QEMU. So we'll compile it, and before I run it, notice actually we're already booted, and we actually presumably have made some calls probably to K3, as you know, and so actually things seem to be working fine. So let's run user tests. And maybe, it's interesting to think a little bit about this. What do you expect? Will this work? Will this not work? Anybody who tried it out?
I think it could potentially lose some pages, but maybe it will not, because maybe a race condition wouldn't occur.
Mm-hmm. Yeah, so one of the things is that these with race conditions, they might not happen. So let's run the user test and see actually what happens. So here we start it up. It'll take a little while. Zoom might complain a little bit because running putting a lot of load on my machine here. Correct, as you probably know, the QEMU is simulating 3 cores here, and these 3 cores might run in parallel. And so far so good. We're starting to pass tests. Definitely a little bit slower because I'm running Zoom at the same time. Let's wait a couple more and just see what's going on. Okay, well, let's just go back to the slides, and then we'll check back in a little while and sort of see what actually happens. But as pointed out, these race conditions may appear, may not appear, right? Because if it's always the case that every core or every time we call K3, these 2U lines are executed atomically as they would have done with the lock, then there's no problem. And the only problem is like if when 2 threads of 2 processors are executed at the same time and something comes in between. And look at this. Actually, while I'm talking, we see actually there is a panic, and so there is some race condition that can actually cause a panic. There are other race conditions that will show up as indeed as mentioned, or as I mentioned, that will show up as like not enough, some free pages or some pages get lost. So basically, user test runs fine until the very end, where it complains saying, well, you lost some pages during all of the runs of user test. Okay. So these race conditions can show up in different ways. They may happen, they may not happen. Clearly something happened here. So let's try to understand, what actually, what goes wrong. Back to the slides. So the picture you should have in your head, so there's this multiple cores that we're running. So here's CPU 0. So CPU 0 is executing instructions, and CPU 1 is executing instructions. And they're both connected, to a memory, right? If you're looking back, think back up at the schematics, that we've shown a couple times before. In fact, there's a DRAM controller, that actually connects, to the DRAM chips where all the state is living, or all the memory is living. So I'm going to make that memory a little bit bigger because I want to have some place to draw. And so basically our free list, lives in memory. And let's say there's a free list with 2 pages on it. Both CPUs, call K3 roughly at the same time. And so look at a little bit at the code again, just to make sure that we have this right in our head. So we look at K3, there get passed in some PA, a physical address that we're going to use to actually hook up, into the free list. So CPU 0 has an R, and that's pointing to some free page, and maybe, and CPU 1 has 1. Let me actually use another color for CPU 1. So CPU 1 has an R. It also is pointing to some page, that we want to hook into the free list. Make sense? And so, we look back at the code. The first thing they do is, update RNext to point to the free list. So let's assume, that CPU 1 runs first, and what it will do is we'll put its pointer, to the beginning of the, to wherever free list is pointing to. And if CPU 1 runs exactly at the same time, then it could run before CPU 0 executes a second instruction, and so it actually might do the same thing. It might actually also run that first instruction and update the pointer too. So now both R's, one from CPU 1 and from CPU 0 and one from CPU 1 are pointing to the beginning of the free list. And the free list is also pointing to the beginning of the free list. And so now there are two remaining instructions that are being executed in parallel. So look back at again, at the code. The remaining instruction that is being executed is actually updating the free list to point to R. And so CPUs 0 and 1 are going to execute these instructions maybe exactly in the same, roughly at the same time, but one is going to go first, correct? There's only one single shared memory, and so one update is going to go first, and the other one is going to go second. So let's say CPU 1 goes first, and now what will then happen? Well, if CPU 1 goes first, the free list is going to be pointing to its R, correct? And then CPU 2 runs, so now CPU 2 runs this X instruction. And so what it's going to do, it is going to actually update, free list to point. So here's our free list, and it's actually going to point to the R that actually it passed in. And so we have a setting now, correct, where we've lost basically one page. The R that actually CPU 0 actually freed actually ended up not being on the free list at all. So we lost the page. And that's one, bad particular outcome. Of course, there could be more bad outcomes because there could be more CPUs actually trying to do this free list. They may observe, one of them may observe the free list pointing temporarily to the CPU 0's R, and so we start using that. Well, then immediately the free list is updated, by the second CPU. So the more CPUs involved, presumably we could actually get more bizarre outcomes than just the lost page. Does this make sense? Any questions? Okay. So the way, as the code does, the way to address this, one way and a very common way to address this problem is to use a lock. So let me talk a little bit about locks in more detail. So what is what's the lock abstraction? Well, it is just an object like any other sort of object in the kernel. And it has in fact, there's something called struct lock, that has some fields, to maintain state about locks. And it has a pretty straightforward API. There's a acquired. In fact, there are only two calls to this abstraction, which acquire, which takes a pointer to a lock struct, and a release, that actually also takes a pointer to the lock struct to basically update, the lock object. And then basically the rule of the rule here is that the acquire enforces this following rule that only one process can enter or can acquire the lock. So at any particular point in time, there's only going to be one process that is able to actually successfully acquire the lock. Any other process that basically is trying to acquire the lock at the same time has to wait until the first process actually calls a release. And so this sequence, the instructions, between, the acquire and the release are often called the critical section. And one reason it's called the critical section is because this is sort of the fused instructions together that do the, need to do the update, to our whatever shared data structure that's protected by the lock in an atomic fashion. And it ensures that basically, if you have multiple instructions in this, between the acquire and release, that they all are executed all together or none. And so there's never the case that basically these instructions in the critical section are interleaved as in the way that we saw in the race condition. And actually exactly that is what avoids these race conditions. Any questions about the lock abstraction? Now, programs typically have many locks. In fact, x86 has many locks. And the reason to have many locks is because even the lock serializes the execution. Right, if two processes want to enter this critical section, only one succeeds, and the other one runs that critical section after the first one finishes. So there's no sort of parallelism at all. So if the kernel had only one lock, which is typically called the big kernel lock, then basically every system call in the kernel would be serialized. You would system call would one start, gets the big kernel lock, does whatever it needs to do, and then releases the big kernel lock, and then basically returns user space. And then the second system call would run. So we have a parallel application that runs, once it runs system calls in parallel, suddenly, all the system calls actually run serially if we had only one lock. And so typically a program like x86 has, many locks because at least, then we can get some parallelism. Because, if, two system calls, for example, use two different locks, then they can actually run completely in parallel without any serialization because they're basically using different locks to serialize. Now, there's sort of a couple of important points. Nobody really sort of enforces in this interface that you put in the acquires and releases. It's up to the program to do so. So if you want some particular piece of code to be atomic, then it's up to the developer to actually put these acquire and releases in. And clearly, as we'll see, and if you can imagine, that is a little bit, it can be tricky. And so it's important to realize that the locking is not actually done automatically for you. It's all up to the developer to figure out to associate locks with data structures and ensuring that the appropriate acquire and releases are there. So clearly, it's the case. Like that locks limit parallelism and therefore limit performance. And so then this raises the question when to lock. And I'm going to give you sort of a very conservative rule, but it's a good one as a starting point to think about things. So the conservative rule, or maybe guideline is a better phrasing, is that if two processes access a shared data structure, and one of them is a writer or an updater, so meaning it's actually going to modify the shared data structure, then you need a lock for that data structure. And so this is a conservative rule, sort of like a red flag. When you're programming and you have a data structure that is accessed by multiple processes and one can be a writer, at that point you should be thinking, okay, there's a possibility of a race condition. We want to avoid this race condition. I'll just stick it in a lock. I will use a lock to guarantee that this race condition can't happen. But this rule is in some ways too strict. There are cases where it's okay if two processes access a shared data structure and one is a writer. In particular, there are sort of styles of programming called lock-free programming that actually totally where these kinds of scenarios actually do happen. And when you want to do lock-free programming, just basically to get better performance or more parallelism. Lock-free programming is tricky. Even more tricky than programming with locks. And we'll talk about it at the end of the semester. We'll study some lock-free styles of programming that particularly are common in operating system kernels. But basically for this lecture, and sort of most of the rest of the semester, we're going to be thinking about the case where using locks, to control sharing. And that is hard enough. Just using locks is not that straightforward either. So it's on one hand a little bit too strict, because it's not always the case that you need it, and also some cases too loose. You might just you might want to lose. You want to actually maybe want to use locks, to enforce some other properties. Like if you look at printf, if we pass a string to printf, the x86 kernel tries to at least, get the whole string to be printed atomically. And there's no shared data structure involved, but it's still useful to actually use a lock in that particular case because we want the output to be serialized. So this rule is not perfect, but it's a pretty good guideline. Any questions about this rule?
I had a question, not about this rule, but isn't it possible that two processes could acquire the lock at the same time and so would be able to modify the structure?
Yeah, no, so part of the sort of contract of the lock abstraction is that it's impossible for two processes to acquire a lock at the same time. If the rule is that there's never a case where two processes actually acquire the lock, can hold the lock at the same time. We'll see in a second how to implement that. But the API or the specification for acquire is there's only one lock holder at any given point in time, or zero.
I see.
Okay, so as we see, programming lock is slightly could be problematic because of these race conditions. Now, of course, the particular race condition that we looked at in K3, or that we created in K3, is easily spottable in some ways. And in fact, if you use a race detection tool, it would immediately find it. But there are more tricky cases. And so you may wonder, why couldn't we make, could we make locks, or could we make locking automatic? So if you follow this sort of simple rule that I just stated, then if ever we see shared data structure, then operations in that shared data structure basically should acquire a lock. We should associate a lock with that data structure, and then every operation that actually that is performed on that data structure basically acquires and releases the lock. So one way to think about it, maybe in x86 terms, like every struct has a lock, and that lock is automatically acquired when we do anything related to that struct. And this turns out to be too rigid, and this is why locking cannot really be automatic. And so in operating systems, an example from an operating system is the following. Let's say we have a call like rename that moves a file name from one directory to another directory. So let's say we have D1X, and we rename it to D2Y. And so we have a file name in the directory D1X, and we rename it to D2/Y. So the way you presumably, if we follow the rigid rule, or like this rule of automatic locking, then what would happen is, that rule, so we have two objects, we have D1 and D2, right? And so we follow the rule, then basically the automatic rule, then we lock D1, erase X, and release the lock for D1. And then we do the second part, update D2, lock D2 at Y, and release D2. And then we're done. So this would be the sort of hypothetical scheme that sort of we imagine would happen if we did automatic locking. And the point of this example is that we'll have the wrong outcome. And why is this a problematic scheme? Why is this not going to work? And so think about like, the thing to think about is like this period. And so we have done the first step, step 1, we're not done step 2 yet. What could another process observe? Anybody?
The file would just be gone.
Yeah, you know, there's between step 1 and 2, the file doesn't exist. And that is clearly wrong, because the file does exist. It's just being renamed, and there's never a point in time really that it didn't exist. But by implementing it in this way, it just appears that a file might actually not exist, even though it does. And so the really right, solution to this is what we need is that we actually lock D1 and D2 first at the beginning of rename, then erase and add, and then release the locks for D1 and D2. Does that make sense? So here's sort of an example where we have an operation that actually needs multiple locks, and the locks cannot really be associated with the 2 objects that are the arguments of this operation. It has to be the case that actually the operation itself first requires the both locks, then performs the operations. And so this automatic locking is not sort of directly possible. There's going to be cases where that this is not going to run to the, or this naive scheme at least will run into problems. Any questions about this?
I have a quick question.
Yeah.
So could we just say that when we're accessing a data structure, we just have to access, or we have to acquire all of the locks associated with all of the data structures we need at the beginning?
That would be one, yeah, so that would be one way of doing it. And I think that this quickly will sort of come down to basically having a big kernel lock.
Oh, I see. Okay.
And then you run the risk, basically, you have no parallelism anymore.
Right.
And so you want to do better than that, right?
Yeah.
And I think this is always the tension. You can make things simpler by basically what's called, coarse-grained locking, but then you lose performance, or you may lose performance, depending if the lock is contented or not.
Yep, makes sense. Thank you.
So lock perspective. So there's different ways to think about locks, and there's sort of 3 common ones, and we'll go for all 3 of them, and just maybe they may help you to think about locks, and then maybe one of them is your favorite, and you can use that one as your way of thinking about it. But it's probably helpful to see that there are actually different ways of thinking about locks. So first of all, one way to think about it is actually locks avoid lost updates or help. If you use locks correctly, locks can help avoiding lost updates. And if you think about our early example in calloc.c, the lost update is basically we lose one update to the K3. And by putting locks in it, we didn't lose that update. So that's one way of thinking about it. Sort of a very low level way. Another way to think about it is, you can make locks make multi-step operations atomic. And so there's sort of the view of a critical section. We have a require lock, we do a whole bunch of steps or instructions, we execute all the instructions, then we release, and basically that whole critical section executes as an atomic operation. And that's sort of and also a fine way to think about locks. And then the third one, that may be helpful is that really what locks do is locks help maintain an invariant. Invariant for the shared data structure that it's protecting. And what really is going on is that before acquire, if there's no lock holder, that invariant holds. When we acquire the lock, and we do some operations, then temporarily that invariant may be violated. But at the point that we do the release, and so if you think about our free list case, the invariant is that the free pointer points to one other next pointer, and all the free pages are on a single list. And that's temporarily violated at the point in the middle of the K-free, because like multiple pointers actually point to the beginning of the free list. And then it's reestablished at the end of it. For the free list, it has a not so complicated invariant, but like for more complicated shared data structures, that can be a helpful way of thinking actually what the lock is doing for you. And so see, even in this sort of the K-free case, all free lock perspectives are reasonable perspectives, and maybe one of them rings more with you than one of the other ones, and use that as your way to think about locks. Any questions about this point? Okay. So I'm going to now run through a couple things, undesirable properties, or that can actually happen with locks. And we know like locks are necessary to fix a correctness problem, to avoid these race conditions. But locks themselves, when inappropriately used, can also introduce their own set of problems. And so I want to talk a little bit about that. And so the obvious one, of course, is deadlock. For example, the simplest case, that's a little bit boring, but maybe worthwhile thinking about. If you do an acquire, a lock, and so you start the critical section, and in the critical section, you do another acquire of the same lock. What will happen? Can the second acquire succeed? Well, with the spec that we've given early on, this should be not allowed. And so basically the second acquirer must block until the first acquirer release the lock. But that was, the process itself. So basically this will result in a deadlock. Now this is a trivial example of a deadlock. And maybe there's interesting, in fact, this is a deadlock that x86 detects, because when it sees that the same process acquires the same lock again, it actually causes a panic. The more interesting cases are when multiple locks are involved. So let's go to our previous example. Let's say we have the following. We have core 1, or maybe CPU 1. We have CPU 2. And CPU 1, executes rename directory 1x to directory 2/y, and CPU 2 executes at the same time rename in the other direction, D2A to D1. When I say B, just to make the names different. So the critical thing to observe here is that CPU 1 runs a rename from D1 to D2, and CPU 2 does exactly the opposite. It does a rename from D2 to D1. So let's assume then that we actually acquire the locks in the order of their arguments. And so what will happen, right, is that in this case, we'll acquire both locks. And we know from our previous example that is actually important. So we'll acquire D1 lock. And let's say they really run truly concurrent. So at that point, this other guy might actually, this other CPU might acquire D2 first, because that is its first argument. And now, of course, D1 wants to acquire D2. So I'll try to acquire D2. Will it succeed? It won't succeed, because the other guy actually has the lock, and so this guy will stop here and not proceed. Now let's look at the other CPU. CPU2 acquired D2. It's not going to acquire D1 for its second argument. It's going to try to call. It's going to call acquire D1, and will it be able to proceed? No, it won't be able to proceed, right? Because the CPU1 actually has to lock in D1. And so here we, sometimes this is called the deadly embrace, where, because in the way we acquired the ordering in which we, acquired the locks results actually in deadlock. Does that make sense, this example? So this is like a little bit more of an interesting example, right, of deadlock. It's not an obvious problem. And the solution turns out, in some sense, reasonably simple. The solution is that, if you have multiple locks, then you have to order the locks, and all operations have to acquire locks in that order. So if you're a system designer, you have to decide, what the global order is for all lock objects. And so, for example, in this case, we might want to decide that D1 should be always ordered before D2. And that means that when we execute a rename, the rule of life is we always acquire the lower numbered directories first before we acquire the higher order directory numbers. And that will ensure that basically there's a global order, and that this particular case just cannot happen because the lock order is going to be then for D1, D2 for this guy, and this guy will acquire the locks exactly in the same global order, D1, D2, and then we don't have this deadly embrace. Does that make sense? Any questions about this? So this indicates a little bit of a problem, right? Well, even though okay, so it fixes this sort of deadlock problem by having global order. And notice this order is global, and this is an issue a little bit when designing a system because okay, hold on. So if you think about the sort of block ordering, that has to be sort of global. And so if one module, 1M, calls a method in module 2, and the caller, M1G, might actually needs to be aware, or could be need to be aware actually of what locks F acquires or what locks M2 uses. Because if M2 uses some set of locks, then if we follow our lock ordering rule, G's got to make sure that if it has some locks, that it acquires all locks from F and G together actually in some global order. And so that really means that the sort of the internals of M2, at least in terms of locks, must be visible to M1. So that M1 can ensure that actually calls M2 in the appropriate way. And in some ways that is sort of an abstraction violation. Right? It's, if abstractions work out perfectly, M1 doesn't really need to know anything about how M2 is implemented. And unfortunately, locks are a common example of where some of the internals of M2 might actually leak out to M1 because M1 really needs to know. And so when you design a bigger system, this makes the modularity more complicated.
Oh, sorry. I was just wondering, does it need to be a complete ordering of locks, or can there be some locks that are that can be ordered in whatever way they?
Yeah, it depends if like F and G, share any locks, right? So for example, if you like look at x86, there are sort of multiple strands of lock orderings because some locks have nothing to do with other locks, and so they're never acquired together. And so if they're never acquired together, they're just joined lock sets, if you will. And then only you have to make sure that the ordering in one particular lock set is global, and the ordering in the other lock set is completely independent of the other ordering. So it is correct that there doesn't have to be a global ordering, but like all the functions that manipulate the same shared sort of lock set, they need to agree on a global order.
Thank you.
Okay, so another sort of challenge with locks, we see now two challenges. One is deadlock, one is modularity. The second challenge, or third challenge, is just locks versus performance. And we already sort of hinted at this a couple times, but it needs to is important enough to sort of actually put some emphasis on. And so basically, if you want to get performance, you need to split up data structures, right? So if you have one big kernel lock, that will limit your performance to basically performance of a single CPU. If you want, performance of you want that the performance scales with the number of CPUs, you got to split up. You need to split up data structures. And the best split, is not obvious or can be a challenge. For example, should you associate a lock with every directory? Should you associate a lock with every inode? Should you associate a lock with every process or not? Or is it better, to sort of split the data structures in a different way? And if you make a change, you sort of redesign the sort of the locking discipline, and got to sort of make sure that you're still maintaining the invariance that actually the kernel is trying to maintain. And if you split locks, basically you also have to rewrite the code, or you may have to need to rewrite code too. And so it turns out that basically you sort of refactor, the parts of your kernel or parts of your parallel program to get better performance by splitting data structure up, introducing more locks. It's a lot of work. You have to carefully think through that you maintain the environments that you intended to maintain. You have to rewrite the code. And so generally, this is just a lot of work and not easy. And so that's sort of a little bit of a negative news point, right? Because we want to get better performance. That suggests more locks, but that is actually a lot of work. And so the general recipe, to how to go about this is to start with coarse-grained locks. And then measure. So whatever, run a bunch of applications on top of your kernel and see whether you get actually any speed up if they actually exploit multiple cores. And if they do, you're basically done, right? Your locking design is good enough. If you don't get speed up, then basically that means that some lock is contended. Multiple processes are trying to get the same lock, and therefore they are serialized, and therefore you don't get speed up. Then you have to rethink about. Then you need to redesign. But the point is that you want to be guided, by these measurements, because it may be the case that some module that uses a coarse-grained lock is just not called in parallel often, and therefore it is not necessary to actually redesign. And since redesign is a lot of work, and it also can complicate the reasoning about that code, then it's a good idea not actually to do that redesign if it's not necessary. And so, in general, a good rule of thumb is start with coarse grained locks, measure whether contention appears in one of these locks, and then redesign that part of the system so that you get better parallelism. Does it all make sense? Any questions so far? Okay, let's look at let's look at in x86 at some code, to sort of understand a little bit how this locking sort of works out in practice in x86. And so I'm going to go back to our this screen. I really need this, and I want to look at UART because we start talking about locking there on Monday, and I want to look at a little bit more in detail now that we know a little bit more about locks, and then also illustrate a couple of interesting points. So first, it turns out, I want to go to, it's looking at lock. It turns out that the UART actually has only one lock. So you can think about this as a reasonable coarse-grained design at this particular point, at least for the UART. And that particular lock, protects basically the UART transmission buffer and the write pointer and the read pointer. And so when we transmit, the write pointer points to the next free slot in the transmission buffer, and the read pointer is the next slot that actually needs to be transmitted. Okay, this is our standard design for parallelism, for consumer producer-consumer parallelism. So let me go back and draw that out. So case study, UART, and there's basically a buffer, and there's a read point, there's a write pointer, or read index and a read index. So this has to go to the UART, being displayed, and this is the writer, or printf, maybe, that actually sticks characters into this buffer. Okay, and so what we can see is that the lock, the lock has multiple roles. One is to basically protect this data structure. And this data structure has some invariants, namely, the read should precede, the write. Anything between R and W are characters that need to be sent. Anything between W and R are things that actually are empty slots. And the locks basically help us maintain that invariant. So here are code again, and let's look at acquires. So here's the UART put C, and the first thing UART put C does is actually grab the lock, and then stick the character, if there's a place in the buffer, sticks the character in the buffer, and starts the printing, and then releases the lock. So if two processes at the same time call UART put C, then this lock will ensure that one character from the first process goes in the first slot, and then the second character of the second process goes in the next slot, and they don't happen to end up in the same slot. Right. So this is like a clear example where a lock helps us to avoid a race condition, because otherwise the second process might overwrite the first process's character. So that's one part. So then if we go look at, we did that a little bit before. If we look at start, we see a couple more things going on. We see actually that if the buffer is not, if the buffer is not empty, then we know that basically there's a bunch of characters that are being progressed or being sent. And the lock make sure that we don't really overwrite any of those. And so anything that's sort of at the tail end of the queue is actually being processed by the UART itself. So tail end is in flight. And we make sure that we basically don't modify or interfere with that particular aspect by grabbing a lock. And then finally, the sort of more and more thing is that the writes to the registers of the UART, like the THR register, of which one there's only one, basically the lock ensures, remember that UART start is called with the lock held, ensures that basically there's only one writer to the TH register. And so another sort of invariant or another aspect that the locking enforces is that hardware registers have one writer. Okay. Now there's one other interesting thing that I want to talk a little bit about, and that is, if the UART is done, correct, the hardware is done, then there was an interrupt. And as you know, we noticed before UART start, correct? We have to the caller. It's on the caller to acquire the lock to ensure that we don't multiple entities are writing to the right register. And so the UART interrupt itself could run in parallel, with another process that's called printf. So we have some process called printf that runs on CPU 0. And on CPU 1 actually takes the UART interrupt, because maybe it's doing nothing, and so it's ready to take the interrupt at any particular point in time, and it will call UART start. And it has to be the case, correct? We want to ensure that there's a single writer, to these hardware registers, or to protect, the invariance actually of the transmission buffer. We have to acquire the lock. And so it is the case that in XV6 actually that interrupts, can run, so the bottom half of the driver can run truly concurrent on different processors with the top half of the driver. And so therefore, interrupt functions also acquire locks. And in fact, in this particular case, it acquires the one lock that there's actually in the UART, and then calls UART start, and then releases the lock. And I'll come back to that in a second, because there's a little bit trickiness in implementing a lock in such a way that this actually works out correctly. And the thing that actually you should be worried about is that, I'll actually talk about it in a second. Let me postpone that until I get there. Okay, so any questions about this sort of simple example of lock use in the UART? Okay, let me, if everything is clear, let me talk about implementing a lock. And so the spec is that only one process can acquire a lock. There's no more than one lock holder at any given point in time. And we now want to look and understand actually how you implement a lock in such a way that that actually is guaranteed. So let me first write a broken lock so that we understand, what the challenge is for a broken acquire. So that we know what the challenge is actually in implementing acquire. So here's my broken one. So broken struct takes an environment, struct lock, star L, and what it does is as follows. It has an infinite loop while one, if L is locked to 0, meaning nobody's holding it, then presumably the caller should grab the lock. So then we set L lock to 1. And at that point we got the lock, so we can return. Nothing to do anymore. And close the loop. If we didn't get the lock, because the lock was 1, that means somebody else is holding the lock, so we just keep spinning. And we wait, go around the loop over and over and over until at some point, the whole lock holder calls release, which will set lock to will set lock to 0. And so what's wrong with this particular implementation?
I think 2 processes might read that it's not locked at the same time. And
Yeah,
then,
right. Yeah, so there's a race condition here, right? And just to make sure that the race is right here. We can have basically 2 CPUs coming in. So if we talk a time diagram, CPU 1, CPU 0, CPU 1. This is statement A. Maybe this is statement B. Both CPU 1, reaches statement A, and CPU 0 and CPU 0 and 1 both reach statement A, so they both see locked being 0, and then they both execute B. Right, so here they see locked to 0. This guy see locked to 0. And so they both execute statement B, and now both have acquired the lock, and which violated the spec of this particular function. Does this make sense? So it turns out, to solve this problem and sort of get a correct implementation, there's multiple ways of going about it. But the most common way is to rely basically on a special hardware instruction. And an hardware instruction that basically what it does this test and this set atomically. And so the solution to this problem is hardware test and set support. And the way you can think about it, on the RISC-V, this instruction actually is the atomic memory operation swap that we're going to be using. And it basically boils down to a test and then a set. And basically what the hardware guarantees, if you will, so we take this, it takes 2 arguments or 3 arguments, an address, a register 1, R1, and a register 2. And essentially what the hardware does, just conceptually, is basically it locks the address, if you will. We'll talk about that in a second a little bit more, but locks address. It puts in a temporary variable, the value that actually is at that particular address. And then writes the value of R1 into that address. And then basically puts the value that was originally at the address into the temporary value that was the original value that was at the address actually into an R2, and then basically unlocks and returns. And this lock, if you will, guarantees that basically this test, where the result of the test is returned into R2, and the set actually happen atomically. And so this is a hardware instruction. Most processors have an hardware instruction like this because it's a convenient way to actually implement locks. And so basically what we've done is we've reduced sort of the atomicity of this or the software lock implementation to basically a hardware lock implementation. So the processor might implement this in very different ways. So basically, the instruction set itself, there's like a specification. It doesn't actually say how it's implemented, and this is very dependent. In the actual implementation of this is dependent on how the memory system exactly works. So, for example, if the multiprocessors share a single memory controller that reads and writes to memory, then the memory controller can actually support this operation. Can basically allow, basically, set a lock in a particular address, and then let, one processor do 2 operations or 3 instructions, and then basically unlock. And so since all the processors, reads and writes go through this memory controller, the memory controller can do the ordering or the blocking. If the memories are in this processor sit on a shared bus, it's often the bus arbiter that can actually do that, where the bus arbiter has support for basically executing 2 memory operations in an atomic way. If the processors have caches, then it's sort of typically part of the cache coherence protocol, where the cache coherence protocol will ensure that if there's a writer, that particular the cache line that holds, the value that we want to update ends up in one single cache, and then basically the processor can sort of lock that single cache line across 2 operations. And so the implementation of this can be done in many different ways, but conceptually what's going on is like you lock the address, you read the original value, you store in the new value, and you return the old value. Does that make sense? To make that, to see how we can use that instruction, let's actually look at the implementation of acquire and release in xv6, and then we'll expose a couple of other interesting details. So let me first bring up spinlock.h. Spinlock.h, as you can see, it's pretty straightforward. It has this flag locked, exactly as in our pseudocode. And then it has 2 other things for debugging, namely the name of the lock and the CPU, the current CPU that actually is holding the lock. And this is mostly to print out debugging messages, for example, if you do 2 acquires on the same CPU. Okay, so then let's look at the implementation. And so let's start out with acquire. And let's first look at this loop. So this is actually the sort of test and set loop that I just talked about. And it turns out that in the C standard actually defines one of these atomic operations. And so the C standard actually has a function that says, sync lock test and set, and basically it specifies the behavior that I just described. And then every processor basically is required, to implement that behavior. And since most processors have a matching sort of test and set hardware instruction, this turns out to be reasonably straightforward for a processor to implement. And so in fact, if you look at kernel.asm, we can look at the assembly instructions and see exactly, what the RISC-V processor does. So in fact, here is our assembly instructions for acquire. And here's our atomic swap instruction. So as you can see, if atomic swap basically is called with the register A5, and as the input, and the output also ends up in A5, and S1 is the holds the address. And if it's not equal, we return, and otherwise, basically, we go back, we jump back to double check I'm saying the right thing here. Move A4 in 6. If not equal, we go to OX20 plus OX22. All right, that's a little bit hard to calculate, but that basically, in one case we branch out, and in the other case we branch back. So this may be easier to just look at the C code. So let's go in here. So what happens? So if the lock is not held, what will be the value of L locked? Well, L locked will be 0, right? And so we call this test and set. What will happen is we'll write a 1 in locked, but we return the previous value. So if the previous value is 0, then we're good, right? Because that means that nobody was holding the lock, and we fall through, and we're done with this while loop. Now let's say the locked value was 1. So the lock was actually locked. Well, what will this instruction do? It will read, the old value, put that at a site, correct? That is 1 actually in this case, and then write a new 1 into that location. But that will change nothing, right? Because the lock was already locked, and the function will return 1, indicating that actually the previous holder, that it was already locked. And so in that case, it's unequal to 0, and so we'll spin, and we'll keep spinning until locked actually is set back to 0. And presume that will happen in the release. Any questions about this? No questions? Okay. So now basically, let's look at the corresponding the release operation, and here's the release operation. And if you look at the kernel ASM again, that instruction. So let's look at the release is probably right after it. Here's release. So the release actually also uses this atomic swap instruction, and putting basically 0 into S1. And so there's a guarantee is basically that this atomic update, to L locked or LK locked, writing a 0 into LK locked is an atomic operation. Many of you ask, why not just use a store instruction to actually write the 0? And anybody may want to guess why that might not work, or what the problem could be?
Because then some other process might be writing a 1 to the log, or no, or writing another 0, but that can't be the case, right?
Yeah, well, there could be, okay, so there could be 2 processes or 2 CPUs writing to L locked at the same time, correct? Yeah. But I think what the question really is that, for many people, and I often assume this too, is that when you do a single store instruction, that is sort of like an atomic operation. And that is not always the case. For example, if you, and it really depends on the architecture implementation. Like, for example, if the cache coherence protocol works, or the cache system works using cache lines, where a cache line may be bigger than an integer, typically bigger than an integer, then really what is happening is the first operation is loading the cache line and then updating the cache line. So in fact, a store instruction basically has sort of 2 micro operations in it, and you can get the wrong result. And so, to avoid, having to understand anything of the hardware implementation of exactly and whether integer operations are atomic or not, or writing to a 64-bit memory value as an atomic operation, we use the RISC-V operation that is guaranteed to be executed atomically. Does that make sense?
Yes.
Good, good. Okay, so just for your amusement, the atomic swap is not the only instruction that exists. So here's the RISC-V manual, and it lists a whole bunch of the atomic operations. So there's an atomic AND, an atomic OR, and there's a max, min, that are all can sort of read and write a value in an atomic operation. Okay. Good. So there's a couple other things that I want to point out in this particular implementation. Let me start again and go back to acquire. So one of the first things that the acquire function does is it turns off interrupts. And it'd be good to understand why that is the case. And so for that, I'm going to go back to our UART example code. And you think a little bit about this. And so we want to think about the case where acquire is actually maybe incorrectly implemented and does not turn off interrupts. So, and the way to think about this is if we go to UART put C, and here, let's say UART put C runs, and acquires the lock, but does not turn off interrupts, what can happen? I'll give everybody a couple seconds to think about it. But if you have an idea or why it might be wrong, jump in.
Perhaps it could be interrupted because of the clock, and then something happens and it needs to print something else, and it tries to do your put C again, but the lock is already taken.
Yeah, that might be a possible scenario. There's a much more direct example for this. So let's just say UART put C, requires the lock, and the UART was basically transmitting some character. So when the UART is done transmitting character, what does it do? It causes an interrupt, correct? And UART interrupt runs. And what does UART interrupt do? It grabs the same lock, that the put C is holding, right? So what will happen here? If there's only one CPU, and so there's no other CPU where this interrupt could be running. Well, we have a deadlock, right? Because the current CPU is holding the lock as part of put C. Then later the interrupt came in, and the first thing it tries to do is actually acquire the lock that's already held. And in fact, in the case of XV6, we'll get a panic, because the same CPU is actually trying to acquire the same lock again. So basically, what acquire or spin lock deals with is sort of two different types of concurrency. One, there's sort of concurrency between two different CPUs. And we got to make sure that, for example, if the interrupt function runs on a different CPU, then basically we don't get a raise on the transmission buffer. But if they run in the same CPU, we got to make sure that it's still atomic and that it's not being interrupted. And therefore, we actually turn the interrupts off in acquire. And they're only turned on again at the end of release when the lock actually has been released. And at that point, it's safe again, to take these interrupts because the lock actually is not released anymore, or is not acquired, holding it, not held anymore. Does that make sense? Okay, there's one more subtle thing in this implementation that I want to talk about, and that we need to deal with. And that is memory ordering. So, for example, if you think about, locked is, let's say, acquire sets locked, to 1. Maybe we have a critical section in which, x is set x plus 1, and then acquire, release, says locked to 0. So you sort of think about the instruction stream that's being executed on a particular CPU, so these are sort of the instructions that are being executed, right? Now, if the code were just purely sequential, the compiler or the processor could actually reorder instructions, just to get better performance. So, for example, if it were a sequential stream, would it be okay to move this instruction to afterwards? Would that change the correctness of the single stream of execution? No, not really, right? Because locked and X are totally independent of each other. There's no relation to it. So it'd be perfectly fine if it were a sequential execution that the X, is moved after the lock 0. So that, on the single serial execution, that's okay. And in fact, processors, do this all the time. They do speculatively execute stuff, or speculatively execute instructions, and so that can result in basically these instructions reorderings. The compiler does it too, to maybe optimize some code path, and also will reorder instructions as long as it results in the same serial execution. But clearly, during concurrent execution, this would be a disaster, right? Because if locked was our acquire, and this was our release, then basically what we've done, we moved the critical section outside of the acquire and release, and that'd be totally incorrect. And so that was wrong. Wrong in a concurrent execution. And so, to forbid or tell the compiler and the hardware not, to do this, there's something that's called a memory fence or something like synchronize. There's an instruction that basically says, like, any loads and stores before this point, you are not allowed to move beyond this point. And so release has this, and acquire has this. And so, for example, this x plus x plus 1, if that was updated after the acquire and before the release, that x plus 1 has to stay before this particular memory synchronization point. And so it will not be, there will be no trouble with memory ordering. And so this is the reason why sync synchronize is there, both in the release, and also there's one in the acquire. Does that make sense?
I have a question.
Yeah.
Is it by convention that the start of the port? So I guess the compiler could figure out that there is an instruction before the lock is even acquired, and that it can be just as well moved after the lock is released.
Yeah.
Can that happen, or will it encounter the barrier and see that?
You will see, in this case, correct, acquire has a barrier and release has a barrier. So anything that happened before locked is set to 1 will happen before that and will never pass that instruction. So this is a barrier. So if you will, this is barrier 1 and this is barrier 2. And so it means that any instruction before here, stay here. Any instructions between will happen between the two, between the acquire and release, and then instruction after, will stay after the release.
Okay.
Okay. Okay, so I'm running, close to the end. So let me just actually wrap up here. So, so locks, locks are good for correctness. But can be bad for performance. Which is sort of a bummer, correct? Because one reason we actually, got into locks is basically to get correctness during parallel execution, but locks actually limit parallel execution. That's one. And two, locks complicate programming. And you will experience that in some of the labs that we're going to be doing. In fact, from now on, we'll see locks showing up all the time. And that will give us, at least, some thought, it's going to be necessary to understand like why the locks are there and, what they protect. But they're sort of inherent if you do parallel programming, that, you need to use locks. And so, if you want to avoid the complications due to locks, is, there are a couple things you could do. Don't share if you don't have to. If you don't have shared data structures, these race conditions cannot happen, and so you don't need locks, and so you don't need this complicated programming. But typically you will have some shared data structures, and you will need locks. And I think the thing to do is start with coarse grained, and then move to fine grained if necessary based on measurements. You want to make sure that the lock is actually contended before you start redesigning. And then finally, use a race detector to one of these race detector tools to actually find problems or race conditions, because you put the locks in the wrong, or you put the acquire and the releases in the wrong place, and in fact you still have races. Okay. So this is a quick introduction to locks. We're going to talk a lot more about locks basically for the rest of the semester that will show up, and we'll talk a little bit more about lock-free programming in the end, and see how that is done in kernels. Okay, so let me stop here. so that anybody who has to go to somewhere else can go. But if you have any more questions, please feel free to ask them.
We have a question in the chat.
Yep.
Isn't the fence instruction unnecessary because the AMO swap instruction can have the acquire release ordering?
Yeah. Okay. So so the two things. There's the sync instructions there both for the compiler and for the hardware.
Yeah, I'm jumping off to start office hours, but I think there's still more questions in the chat.
Yeah,
Like, how do you do it for the compiler only?
The compiler knows for which architecture it's compiling, and so it will know whether it actually has to insert the appropriate fences, for whatever architecture it's running on and whatever memory consistency model it has. So this gets into a little bit more complicated discussion. Is that every piece of hardware has a memory model, and and the compiler has to decide, given the memory model for that particular architecture, what actually it can do and what it cannot do.
And I guess my question was that, like, the fence instruction only becomes unnecessary if you call ammo swap like .w.release, and like putting in the sync in there that will sync both the the compiler ordering and then the memory ordering and the out of ordering machinery using the fence instruction as well. The fence instruction is only unnecessary in the case that you do .rl. So it seems like it wouldn't detect that. So how would you do it? So the compiler enforces the ordering on its end, but you already cover it using the ammo swap instruction.
So like if you, it's a very good question, and some more sophisticated acquire and release implementation would be more like a specialized acquire or release implementation or release implementation for RISC-V. We would probably do more sophisticated things than we do, where we're pretty, of course, grained by just issuing that fence instruction. But it's slightly complicated, and so if you're interested in this, the memory model for the RISC-V is reasonably complicated. So if you look at the instruction manual for the unprivileged instructions, there's a whole chapter dedicated, to memory ordering, and tells you what the compiler should do in this particular case.
So you're saying that the compiler would pick up on the fact that we just put that assembly instruction inside of there, and it wouldn't reorder any of the memory accesses on its own?
Sorry, this synchronized library function is a library function, right? And it can be implemented in different ways. And this is one particular implementation. And the library function is provided by the compiler. So,
but is there like the option for the compiler to do optimizations where it itself moves the loads and stores around?
Yes, compilers do.
So how do you prevent that without emitting the fence instruction? That's what I was curious about.
I guess what I'm saying is that what I'm saying is that basically this indication, the synchronize, basically both tells the compiler and the hardware, but the compiler could actually implement synchronize differently. It knows that it can't move things around, but it doesn't have to issue a fence instruction on the RISC-V. It knew that it was running in a particular way on RISC-V.
But isn't the RISC-V memory model like loose enough to where the out of order machinery could reorganize stuff? So you do need like the acquire, like the whole point of having.
Okay. So they're more complicated interfaces than synchronize, and which give the compiler writer more, it gives the programmer more freedom, and will give the compiler and sort of decouple the compiler part and the processor part. So, for example, I think there's a flag that you can pass in, to say that this is release consistent synchronize. I don't know the details right out of my head, but if you look into this, this is sort of the coarse-grained interface, and there are more fine-grained interfaces that give the programmer more control.
Okay, thank you.
I have two questions. One is, how do you, for having multiple threads on one processor, do you argue in roughly the same way as we did for multiple processors?
So can you repeat that question just to make sure
So we didn't. I don't think we really talked about multiple threads. We mostly talked about multiple CPUs. So for multiple threads, is the I guess the solution the same as for when you have multiple CPUs? Like, do you have the same arguments there?
More or less, at least conceptually is the right way to think about it. So if you have multiple threads, but only one CPU, it's still the case that you want to ensure that certain kernel code sequences are executed atomically. And so you still have to have a notion of critical sections. You might not need locks or releases explicitly, but you do need a way of sort of turning on interrupts off and on in a particular piece of code. So if you look at older operating system kernels, they typically don't have really lock and acquire in the kernel because they assume they're running on a single processor, but they do have something like locks, to basically turn off interrupts on and off.
Okay, I see. And my other question was actually on the slide with the UART picture, the buffer.
Let me go back.
Yeah, is it? Yeah, that one. Is it always the case that the read is going to be like lagging behind? I didn't understand that.
Yeah. Okay. So so this goes to the display. Yeah. Whatever is in this, basically this is the sequence of characters that needs to go to the display. And the writer basically is appending more and more characters. Right. And so so the writer is going that way, and basically the reader's following the writer, right? Because it can't print a character that hasn't been put into buffer yet. And so the UART that puts things on the display, will start basically putting the first character that's in this slot onto the display. Meanwhile, printf could come in, and multiple printf come in. That they put more characters in here, so that the right pointer is basically standing here. And then when this one character is displayed, then the UART will move up this pointer to display the next character. Right, so the UART is always lagging a little bit behind the writer until the point that it catches up, right? And where R and W are the same, and at that point, basically, that means that there's no character anymore in the buffer.
Oh, okay, I see. That makes a lot more sense. Okay, thank you so much.
You're welcome. Any more questions?
Just us left here.
Okay. Okay, guys. See you later.